Hey, this is Mr. Eaton. This is Chemistry Honors, and this is the equilibrium constant. We just figured out what chemical equilibrium is. Chemical equilibrium is our two definitions: when the rate of the forward reaction is equal to the rate of the reverse reaction, and it's when your reactants and your products stop changing in concentration. That's when we hit chemical equilibrium. It doesn't mean our reaction has stopped, though. Our forward reaction, our backward reaction are continuing to go forever. It's in what we call dynamic equilibrium. Well, we have this thing called the equilibrium constant, which we call K. And you can see right here, it says the equilibrium constant, which is our K, because constant begins with the letter K, obviously. You can see our products are over here, and our products go on our numerator, and our reactants are over here, and our reactants go on the denominator. So it's pretty easy. You just put little brackets, and you put your products on your numerator. Remember, when they're being added, our products, they're being multiplied in my equilibrium expression, okay? And then any coefficients you have, like let's say this is 2 of these guys, it is going to be squared, so that will be an exponent, and that is called the equilibrium constant. And something to note is this is the most important note, solids and liquids are not in your equilibrium expression since they don't have concentrations. So only aqueous solutions and only gaseous solutions will be in my equilibrium expressions. And so that is called the equilibrium constant. And we call that K. And just keep in mind, it could be Kc, which means concentration. It could be Kp, which means pressure. It could be Ksp, which means solubility product. It could be Ka, which is acids, or Kb, which is bases, or Keq, which is the equilibrium constant. These are all the same. They're all the same. It's all the same. Okay? So let me show you a few examples. So here we have N2O4 gas in equilibrium with 2NO2 gas. And so what are we going to do? Our K expression is going to be our products is going to be on the top, NO2. And that 2 becomes squared divided by our reactants of N2O4, and that's only one of them, and that is my equilibrium constant. Now here you can see the next one. This is a solid. We do not put solids or liquids in my equilibrium expression, only the aqueous or gases. So here we have K, and you can see we have silver positive 1. It's on Ag. It's silver positive 1 times chloride negative 1, and that is my equilibrium expression. You can see here, this is a famous one. This is called the Haber process. You can see for my K, I'm going to put the NH3 on my numerator, and he's going to be squared over my N2 gas times my H2 gas. And what is that H2 gas? To the third power. And so that is my equilibrium constant. Again, do not put liquids or solids in there. One last example, if I have, let me just think of it, let's say I have HF plus, then that is going to be, I'm going to do some states of matter, so it makes sense. Aqueous plus H2O liquid, we've seen this one before. He gives away the H plus, and we get H3O plus, which is aqueous, plus your grade, F minus, which is aqueous. Oh, hopefully not your grade. And how are we going to do the K for this? Well, we're going to put the H3O plus on the numerator times the F minus on the numerator over my HF. What is not going to be there is the H2O because it is a liquid. A liquid. Okay? That's the equilibrium constant. Now, you're probably asking, what in the world does this mean? I can do it. I have no clue what it means. So let's take a look. So, what do you know? Here is that equilibrium expression. So you can see that we have your K is going to be the F minus times the H3O plus over the HF. Okay. Now look at this K. This K says 0.00072. Is that big or is that small? That is really, really, really small. That's a small number. That K is less than 1. So if the K is less than 1, what does that mean? Which is bigger, your numerator or your denominator, if your K is really, really small? That means your denominator must be really big comparatively. That means your numerator has to be really small, which means this reaction stayed over here at the reactants. It did not go to the right to the products. It stayed to the left. The reactants are what we call favored. And think about it, HF is a weak acid. What do weak acids not do? Weak acids do not dissociate, do they? They stay HF. So that's something that confirms something we've learned before in acids and bases. Let's take a look at this next one. This next one, we have our K is equal to the barium, plus 2, times the sulfate, negative 2. And look at this K. Is this K really, really big or really small? It's 1.5 times 10 to the negative 9. That's 0.00000000015. That is really small. That K is less than 1, which means who is favored if the K is really, really small? The reactants are favored, which means this will not split up. This will stay as a solid, which means barium and sulfate, if you put them together, they will become a solid or precipitate because the K is really, 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 really small. Now let's take a look at this next one. This K is going to be equal to the nitrogen gas times the oxygen gas over the NO squared. Look at this K. It's 1 times 10 to the 31st. That's 1,000,000,000,000,000,000,000,000. It's really big. Okay, that K is really much greater than 1, isn't it? So who's going to be greater? The products are going to be big. The reactants are going to be small, which means which way did this reaction go? It went this way, which means the products are favored. This reaction will almost go to completion. Now remember, it doesn't go to completion. There's still at least one particle of NO in there because it's got to be at equilibrium, but the products are favored. So if the K is really small, it indicates the reaction really doesn't go forward. It stays our reactants. If our K is really, really, really big, it means our reaction goes to almost completion. It means the products are favored, and that is what the K means. It tells us how our reaction progresses, whether it progresses or whether it doesn't. And that is called the equilibrium constant.